Hi my dear students, today we will learn about electric field lines and flux. In our previous classes we learned about Coulomb force, principle of superposition and electric field. Then we studied that if you know all these things, you can analyze electrostatics. Okay, but there you will see that if you want to find out electric field of a simple system, then only you have to know integration very well. The integrations are very, even for simple systems it looks more tough. So, in this section onwards, we will learn about tricks or shortcuts to avoid these type of integrals and find out the electric field of the system. Once you know the electric field of the system, you can find out the Coulomb force in it. Because we already learned that through the electric field, the one charge knows about the presence of the other one through the electric field. Okay, so once you get this electric field, you can find out Coulomb force. So, in this session onwards, we will discuss many tricks to avoid the integrals in this electric field and find out electric field easily. Okay? Now, before moving to these things, first we have to discuss about field lines. We already learned that the presence of electric charge is communicated through the space through the electric field. Okay? So, consider a point charge Q like this. This is a point charge Q, and from this there are field lines like this. Okay, this is point charge Q. I can write it here like this. Okay, these are all different field lines. But you know that here, in the case of a point charge Q, the electric field is given by 1 by 4 pi epsilon 0 Q by R square R cube. Right? So, these field lines radially outward and its magnitude decreases by 1 by R square. So, we can assume a field like this, okay, pointing radially outward. As it moves away from this charge, its length gets reduced, just showing that its magnitude reduces. Okay. Similarly, you can draw here also like this. Okay. Now, as it moves away from this charge, its length reduces, to mention that its magnitude gets reduced, right? Like this. Okay. Similarly here also. Then you can draw as many field lines as you want. When we express these type of magnitude representation. Okay, so instead of this type of reducing this arrow's length as it moves away from the charge, we can represent the field lines by single lines, just like this. This is another way of representing the field lines of charge Q. Like this, you can draw field lines like this. Now what happens? Now you feel that its magnitude has no role in this figure, right? But it is not the right way of saying all these things. The thing is that the field line starts from this point charge, and as it moves away from this point charge, its density gets reduced. Okay? Field lines moves away from field lines ends on negative charge. Okay, field lines moves towards the negative charge. Here, we assume here positive Q plus QQ. So the field lines moves away from the charge. At the same time, if you represent this charge by negative minus Q, the arrow pointing towards this charge. Okay, that means field lines moves towards the negative charge. Here it is positive charge, so it moves away from the positive charge. Okay. The another point about these field lines are field lines never intersect each other. Then what happens if they intersect each other? Then there is two directions for a particular point. It is not possible. Electric field has only one direction at a point. So the field lines never intersect each other. Okay. Field lines never intersect each other. Okay, field lines never intersect each other. Now we want to know how we can represent the strength of this electric field. Okay, the strength of the electric field, the strength of the field is given by the density of the field lines. Okay, the density of the field lines. These are called field line. Okay, this is one field line, this is another field line, like that. Okay, there are so many field lines. Now, the strength of the electric field is proportional to the number of field lines passing through a particular area. For example, suppose you want to check field lines through this area. Okay, I can show you here. It's another. This is the, suppose this is our area. Okay, now we want to know what. Now, the strength of the electric field is given by the density of the field lines. For example, consider a small area like this. You can see that as far as this area is nearest to this point charge, now there are two field lines passing through this area. Okay, but as it moves away from this point charge, the field lines moves like this. Okay, this field line moves like this. Now, if you check the same area here in this conductor, it moves like this. You can see that the same area here, there are only one field line. As it moves away from this point charge, the number of lines passing through this particular area get reduced. Hope that you get the point. Okay, that means as the field lines moves away from the point charge, the electric field intensity gets reduced. Right? This is the equation. So, as we move away from the charge Q, the electric field gets reduced by 1 by r square. That means, if we move away from this point charge, for a particular area, you can see that the number of field lines passing through the area get reduced as it moves away from the point charge. Okay, so this representation is also included the strength of the field, but here we describe the strength of the field by the number of field lines passing through a particular area, or the density of field lines. It is called here the density of field lines. can draw the field lines here. For example, suppose there are two positive charges like this, plus Q here and another plus Q here. Okay, these are the two charges. And we already found that field lines moves away from this point charge. So these are the field lines from this charge like this. Okay, and in this it moves like this. And here this moves like this. Because these two are positive charges and the field lines always moves away from positive charge. Okay. And so this field lines actually extends up to infinity. It can never terminate in between. Okay? It cannot terminate in mid-air, but it can start from a positive charge and extends to infinity. Or these field lines can start from a positive charge and ends on negative charge. Okay, so if there are a plus positive Q and a minus Q like this, plus Q and minus Q, electric field line starts from this positive charge and moves to this negative charge like this. Okay. Like this. Okay. These are the nature of field lines. Electric field line starts from positive charge and either extends up to infinity or ends on negative charge. It can never terminate in mid-air. Okay. Similarly, electric field lines can never intersect each other, because if they intersect each other, there is two directions for a particular point. It is impossible. Okay. So electric field lines never intersect. Okay, these are all the important things about this electric field lines. Now, we already found that the strength of the electric field is given by the number of field lines passing through a particular area. Okay, now we can define the flux. Okay, flux. It is a measure of field lines. It is a measure of field lines. And the electric flux is defined as phi E equal to surface integral of E dot dA. If dA is the area, then the surface integral of E dot dA gives you flux. You can understand this equation from here itself. We already mentioned here that the strength of the electric field is given by number of field lines passing through a particular area. Here you can see that this flux is defined like this: surface integral of E dot dA. This E dot dA represents number of field lines passing through infinitesimal area dA. Okay, passing through infinitesimal area dA. Okay. Now, so this surface integral E dot dA gives us the total number of field lines passing through an area S. Here you can remember one more thing. This area is considered as perpendicular to the electric field. Because you know that we take here dot product. This area vector is always perpendicular to the area. Direction of the area vector is always perpendicular to the area. So this vector should be oriented along the direction of electric field. Okay, so we consider the area such that the plane is perpendicular to the electric field. Now what happens? This definition, the surface integral of E dot dA, gives us the total number of field lines passing through the surface S. Okay, I think you get the idea of the flux. Flux means the number of field lines passing through a particular area. Here E dot dA, surface integral E dot dA gives us total number of field lines passing through the surface S. It is defined as electric flux. Now we can extend this concept a bit more. Now consider a closed surface. Okay? Then what happens? The charges inside the surface, there are field lines from the charges inside the surface. They passing through the surface outward. Right? For example, suppose there is a surface like this. For simplicity, we can assume a closed surface, spherical surface. Now there are a charge Q here. Okay, we already learned that there are electric field lines from point a charge Q. So here also there are field lines passing like this. Okay, there are so many field lines passing through like this. Now the number of field lines passing through this closed surface. Okay, so the flux through this closed surface is equivalent to the total charge enclosed by the surface. Right, because all the field lines are emanating from the charges inside this surface. Okay, so here you can define this flux as flux is equal to the total charge inside the surface. So now you can write the points here. That's the first point is the flux through any closed surface is a measure of total charge inside. It's a measure of total charge inside. Okay. Now, how can we prove this thing? One example is, if suppose there are positive charge inside the surface like this, then field lines emanate from this positive charge and moves out, passing through this surface. Okay. Now, suppose instead of this, there is negative charge inside. Okay. Instead of this, I can show you here the different situations. First one is positive charge, and there is a spherical surface here. Okay, spherical surface here. Now the field lines are like this. Because this charge is positive charge and so the field lines moves away from this charge. This is the surface S, this is the surface S through which this field lines passes out. Okay. Now, instead of this, suppose a negative charge inside this surface. Okay. There is a negative charge minus Q. Then we can assume a surface again here, spherical surface for simplicity, and the electric field lines moves inward. Okay. Electric field lines moves inward like this. Okay. All these field lines passing through this surface S. But this time, this field lines pointing towards the my negative charge. Okay. Now, suppose that there is no charge inside the surface. Okay. Then what happens? For example, our surface is here. This is the surface. There is no charge inside, but there is charge outside. Here there is Q charge. Now what happens? The electric field lines passes through to here like this. Okay, so electric field lines come inside and goes outside. Okay, like this. Because how many field lines enters, that much field lines goes out. Okay, so there is no flux through this surface, Okay, this is the surface. There is no flux here. In this conductor, there are flux because all the field lines coming to this negative charge. In this case also there is flux because all the field lines passing out from this inside to outside. But in this case, there is no flux because how much field lines enters into the surface, that much field lines goes out also. Okay, so we can conclude that the flux through any closed surface is a measure of total charge inside. I think you get how can we measure this thing. Okay, now you can quantitatively find out this. For that, we already defined flux such that electric flux equal to surface integral E dot dA. Now consider a spherical surface and a point charge. Okay, so in that context, for a spherical surface, the flux is given by the surface integral of E dot dA. Electric field is due to the point charge. In this context, you can see that there is a point charge Q. Okay, then the flux through this surface S. This is surface S. Okay, so the flux through this surface S is given by surface integral of E dot dA. E is given by Q by 4 pi R square R cap. Now dA. dA is also along the direction of R cap. So for a sphere, you can write this radial element R square sine theta. I think I can write it in the next line. Okay. This flux phi E equal to surface integral of electric field 1 by 4 pi epsilon 0 Q by R square R cap theta, d theta, d phi r cap. You learned about this aerial element earlier. In this case, this aerial vector should point along our radial direction, r cap direction. So the corresponding aerial element should be like this: r square sin theta d theta d phi. Okay. Now this integral is over sin theta d theta and d phi. You know that in spherical polar coordinates, in the case of theta, this integral runs from 0 to pi, and in the case of d phi, it runs from 0 to 2 pi. So this integral gives you 4 pi. Sin theta d theta d phi gives you 4 pi. R square and r square gets cancels out. So you get here q by epsilon 0. Okay, q by epsilon 0, because sin theta d theta d phi equal to 4 pi. 4 pi and 4 pi cancels out. R square and r square cancels out. You have left with q by epsilon 0. So what we get? The flux through a surface S is given by the charges inside. Okay, charges is a total charge enclosed by epsilon 0. Okay, this law is called Gauss law. This law is called Gauss law. We can state the Gauss law as the flux through any surface enclosing the charges q by epsilon 0. Okay, the flux through any surface enclosing the charge is q by epsilon 0. This is called Gauss law, and in equation, mathematical form, you can write this Gauss law as phi e equal to surface integral of E dot dA equal to q by epsilon 0. Actually, for deriving this, for reaching this equation, we assumed a spherical surface. But you can extend this to any arbitrary surface, but a closed surface. Okay? If the surface has a shape like this, but still the surface is closed, the number of fluid lines passing through this surface always gives you the flux. And this flux is always equal to the total charge enclosed. Okay, so this Gauss law is defined for any arbitrary closed surface. For any arbitrary closed surface S, E dot dA equal to the charge enclosed by epsilon 0. For closed surface, you can make a circle here to represent surface integral over a closed surface. Okay, so here this surface represents any closed surface. Any closed surface. Okay, so the flux through any closed surface is equal to q by epsilon 0, corresponding to the charge enclosed by the surface. Okay, this is called Gauss's law, and since this Gauss law can be applied to any type of surfaces, this has many applications. Before moving to the applications of Gauss law, we have to actually see that this Gauss law is in the form of a integral, okay, closed surface integral, and we already defined this Gauss law for a single point charge, writing this q here. Now, suppose there is a system of charges, okay, system of charges. not a single charge, a bunch of charges Qi. Okay, where I equal to 1, 2, 3, etc. up to n. Okay, then we already learned that using principle of superposition, you can find out resultant electric field, and electric field is given by sigma I Ei. Okay, this is the electric field. Now, in order to get the flux through the surface, you need closed surface integral sigma I Ei dot dA. Okay, or you can write this as sigma I closed surface integral Ei dot dA. And now you can write this as surface integral of E dot dA. This is equal to sigma I Qi by epsilon 0. Okay, because here you can see that Ei dot dA is replaced by Qi by epsilon 0. So this summation runs over all these terms and you get total charge enclosed by epsilon 0. Okay, so for a system of charges, the electric flux through any given closed surface is given by charge enclosed by epsilon 0. This charge enclosed is obtained by adding all the charges inside the surface. Okay, this is for Gauss's law for a system of charges. Now, you can write this Gauss law in the form of a differential equation. Okay, so I can write here differential form of Gauss law. Differential form. Now, in our first chapter when we learned about mathematical tools, we learned about Gauss divergence theorem, right? From there you can see that the surface integral over any closed surface of a vector field can be replaced with volume integral of divergence of the vector field. That is called Gauss divergence theorem. Okay, using Gauss divergence theorem, surface integral of E dot dA equal to volume integral of, here the vector field is electric field E, so divergence of electric field and its volume integral. Here the elementary volume is considered as d tau. Okay, using this equation you can write the Gauss law in new terms. Instead of this closed surface integral, now you can write the volume integral del dot E d tau equal to Q enclosed by epsilon 0. This is the more general equation. Okay, Q enclosed by epsilon 0. Or you can write this as simply by Q. You write here as Q. From this equation, you can write this like this, Q by epsilon 0. Now, this side is a volume integral, so you can convert this side also in the form of a volume integral. Okay, for that you can write this Q in terms of charge density. So you can write here 1 by epsilon 0 volume integral of rho d2. This rho represents volume charge density. Okay. Now what happens? Now you can compare both sides. Both sides there are volume integrals over same volume V with the elementary volume element d2. So from this you get del dot E equal to rho by epsilon 0. Del dot E equal to rho by epsilon 0. Rho is called volume charge density. We learned it about in our previous classes. We discussing about this continuous charge distribution. Okay. So rho represents volume charge density. In terms of rho, Gauss law can be written like this. Okay. Del dot E equal to rho by epsilon 0. Okay. So these are all about field lines, flux and Gauss law. So you can write Gauss law either in the term of integral form, closed surface integral, or in the form of differential equation. Okay. Divergence of electric field. Del dot E equal to rho by epsilon 0. So for a given surface, the electric field lines passing through the surface is given by the total charge enclosed by the surface divided by epsilon 0. Okay, this is called Gauss law. Okay. Now we want to check how can you find out this divergence of electric field. Before that, you have just remember what we learned here. We learned here about field lines, then move on to flux. Finally, it extends to Gauss law in integral form and Gauss law in differential form. Okay. Now, we know that del dot E represents divergence. We want to find out divergence. So, first of all, we want to write electric field. Okay. Electric field is given by, the electric field is given by 1 by 4 pi epsilon 0 Q by R square R cap. Instead of this Q, I can write here the volume charge density rho. Okay, so I put here rho R prime d2 prime to just mention that this volume integration is over the prime coordinate. Okay, rho R prime d2 prime. We already know that this unprimed coordinate represent the field point, but here the variation is to this charge density rho, so we have to put prime here. So to represent this volume integration is over this primed system, I just put d2 prime here. Okay, so this is the equation. Now we want to take this divergence. So del dot E equal to 1 by 4 pi epsilon 0 integral del dot R cap by R square rho R prime d2 prime. Okay. Now we know that this operation, this del dot R cap by R square gives us 4 pi del cube R, where this del cube represents three-dimensional Dirac delta function, and here you can write this as 4 pi del cube R minus R. Okay, 4 pi del cube R minus R. you substitute it here and you get that del dot E equal to 1 by 4 pi epsilon 0 4 pi del cube r minus r prime rho r prime d dot prime. Okay, this integration is over. Volume V. Now you get from this expression 4 pi rho of r by epsilon 0. This is the Gauss law in differential form. If you need its integral form, you can apply Gauss divergence theorem such that volume integral of del dot E d tau is equal to closed surface integral of E dot dA. In reverse order, you can apply this, then you get this del dot. Instead of this del dot E, you can apply rho by epsilon 0. This gives you Q enclosed by epsilon 0. Anyway, the divergence of the electric field is given by this differential form of Gauss. Okay, now I think I can wind up this session here. In this session, we learned about electric field lines. Then we mentioned that you can show the direction and strength of the electric field using the field lines. Field line starts from positive charge and either it extends to infinity or it ends on negative charge. It can never terminate in mid-air. Okay, remember that thing. Then we mentioned another thing is field lines never intersect each other. Okay. Now we use these field lines to represent the strength of the field. The number of field lines passing through a particular area represents the strength of the field lines. So we use this concept to represent the strength of the electric field, which is called here flux. Okay. Now the flux is defined as closed surface integral of electric field. Now using this concept, we find out that this flux is equal to the total charge inside the closed surface. This is called Gauss law. Then we write it in integral form and in differential form. Finally, we move on to the divergence of electric field and again show that if you find out the divergence of electric field, it gives you differential form of Gauss law. And applying Gauss divergence theorem, you can get the integral form of Gauss law. Okay, so learn well. Thank you.